Hello and welcome to another video. In this video we're going to be working on find the original array of prefix XOR. And in this problem you're given an integer array prefix of size n and you want to find and return the array r of size n that satisfies prefix I equals XOR of all the numbers up to I. Note that this denotes bitwise XOR. It can be proven that the answer is unique. And so for the first example we have prefixes 5, 2, 0, 3, 1, and our output should be 5, 7, 2, 3, 2. And let's quickly show how we can get that. So for the first number, it's just going to be the same, right? So here's our prefixes and here's our numbers. So for the first number, the prefix is only this number. Then for the second number, it should be 5 XOR 7. And so if you actually do 5 XOR 7, then you would get this. And remember in an XOR, 0 with 0 gives you 0, 0 with 1 or 1 with 0 gives you 1, and 1 with 1 gives you 0. So here if we XOR these, we get 0, 1, 0, which is 2. So this is 2. And then 0 is 5 XOR 7 XOR 2. So we already did 5 XOR 7. So now we can do XOR 2. And XOR is an operation much like add, where if you have some previous thing, you can use the old one and just add the new one. So kind of like addition, right? Like if you have 2 plus 3 plus 5, you can just say like, well, if I have 2 plus 3, let me just take that result and add 5. So that works. So it has that property. And for the third number, we have 0, so it should be 5 XOR 7 XOR 2, like I said. So we have a 5 XOR 7, so let's XOR with 2. And this XOR is in fact 0, so that's why it's 0. Then for 3, we need to XOR with 3. And we do get 3. And finally, for this 1, we need to XOR whatever we had with the 2. So if we XOR this with a 2, then we get 0, 1. So this is indeed correct. This is the prefix XOR of these numbers, right? So each index represents the XOR of all of the numbers up to that index. So 2 is XOR of all of these, 0 is XOR of all these, and so on. And they do say the answer is unique. So let's actually use an easier example to kind of understand this better. Let's say we have 52031, but instead of prefix XOR, let's actually use prefix sum. So let's say this was a prefix sums array. And what a prefix sum means is it just means that the element at some index is the sum of every element up to that index. So we need to make an array of elements where the prefix sums of this array is this. Let's try to do that first and try to kind of get intuition. And then from there, we'll do prefix XOR. So essentially for the first element, the prefix sum here, we'll call it prefix sum, is the sum of every element up to this index. So that means there's only one element to start off, so this has to be 5. Now this is the sum of every element up to this index, so that means with 2 elements, with the first one being 5, what does the second element have to be for the sum of every element to be 2? Well, it has to be -3, right? Because the sum of these two is 2. Then with an array of 3 elements, how do we get a total sum of 0? This has to be -2. Then how do we get a total sum of 3? We can add 3, and how do we get a total sum of 1? We can subtract 2. So you can see how like there's a recurrence relation here where prefix sum at I equals prefix sum at I minus 1 plus whatever this array is, array at I, right? So like we start off with just, the same element, but here to get this element has to be the one before, right? That's the previous sum plus the new element we added. So -5 plus, or 5 plus -3, 2. And then this 0 has to be 2 plus -2. And then this has to be 0 plus 3 and so on. So that's how it works with prefix sums. And prefix XOR has to work kind of the same way because it has the same properties as sums where you're just essentially keeping track of a total and then you're adding this new element. So for prefix XOR, let's call that X for this. Let's try to also get some intuition of how we can get these numbers. Because for some, like we know we can just do a subtract and it's pretty straightforward, right? But how do we actually do this with XOR? So let's have this array. So we know the first element has to be the first number in the prefix XOR, right? Because the prefix XOR at index 0 is just whatever the first element is, right? Because there's nothing to XOR, it's just the first element. So we know that, that's like a given. But what does the second number have to be? And so to figure out what the second number has to be, notice we can have that same equation where prefix XOR at I equals prefix XOR at I minus 1 XOR A at I, right? It's the same kind of thing. Like it's cumulative. You can add them together. And so here for this equation, so prefix XOR at index 1, so 2 equals prefix XOR at I minus 1 is 5 XOR with some integer, right? So let's just try to figure out, and they say the answer has to be unique, so there has to be like a unique integer to get this. So let's try to figure out what this has to be. Let's try to get it. And the way we're going to do it is we're going to just show the binary representation, and then we're going to figure out what it has to be. So we have 5, which is 0, 1, 0, 1, XOR with something equals 2, which is 1, 0. So what do these bits have to be for these XOR'd to be this? So 1 XOR'd with something to make it 0, 1 XOR'd with 1 is 0, right? So this has to be 1. 0 XOR'd with something is 1, so this has to be 1. 1 XOR'd with something is 0, so this has to be 1. And this has to be 0. So this is the number that we have to have, right? Now you can, obviously, so what you can do is since you're given this and you're given this, you can do like a bit by bit operation, just be like, okay, well, if this is 1 and this is 0, then this has to be 1, and so on. And you can build up your number bit by bit. But let's see if there's any way we can actually shorten the process. So if this number is 2 and this number is 5, how do we figure out this number? Like, is there anything we can do? Like, can we use these two numbers somehow to get this number? Do you see anything, right? Like, think about it for a second. Is there something I could do with these numbers bitwise? Like, can I knot them? Is there some operation? And it actually turns out that there is a way to do it. So if you actually do 5 XOR with 2, let's see what we get. So we actually get 0, 1, 0, 1, and 2 is 0, 0, 1, 0. So if we actually XOR these, we get 1, 1, 1, 0. So we get this middle number. So if you write an equation of like A XOR B equals C, well, actually, if you're solving for B, then C XOR A also equals B, right? The way it works is if one number and XORing another number is a third number, then you can get this middle number by just XORing the other one. And this works with a bunch of numbers, and you can try this with a bunch of numbers. So that's the equation we have. So now we can actually solve for these things, right? So now we can solve for like, what is AI? Like, let's basically take this equation and let's rewrite it, because the element we don't have is AI and we have the other two, right? So notice this pattern once again, A XOR B equals C. That means C XOR A also equals B, right? You can flip these around freely as proven here. And you can try this, like I said, with a bunch of different things, but essentially that's how we worked it out. So this would be 5 XOR 2 equals 7. So essentially you can swap these around. And so now we can rewrite this equation, and then we have two of these variables. We just don't have AI. So let's have AI separately. And we can write it over here. So we can say AI equals PXI XOR PXI minus 1. Right? Like what we did here. Same thing. If A XOR B equals C, and we're solving for B, then B is C XOR A. So we can just move this to one side. So for the number, for every number, like let's say we're trying to get this number here. Let's try to use this equation now. So we have this 5. Now we're going to say, okay, well, for this index, so let's write down all these indices as well. So we're going to have index 0, 1, 2, 3, 4. So for AI, it's PXI, which we are given 2, XOR PXI minus 1. So it's 2 XOR 5. And we did this earlier, right? 2 XOR 5 is 7. So here we have 7. And now for the next number, it's going to be 0 XOR 2, and any number XORed with 0 is just going to be that number. So this is 2. Then we have 0 XOR 3, same thing. Any number XORed with 0 is going to be just that number. And then 3 XOR 1, so 3 XOR 1 really quickly is going to look like this. And if you XOR them, it's this, which is 2. So we can basically use this equation. So to get some index at an array, it's just the current index in the XOR array XORed with the one before. And the starting element in the array is 5, or whatever the starting index is. And that's basically it. So you can literally just loop through your array, compare these two things, XOR them, and then get the number. And if we look at our results, so we have 57232, and this is 57232. And yeah, the way like I honestly didn't know this like XOR switching. I just literally looked like, okay, I have a 5, I have a 7. What do I need? And is there any kind of bit manipulation trick I can use to make this happen? And so then I realized, okay, well, I can just XOR other numbers, and that's how I would do it. And that's like the intuition. It's not super easy to get, but I think it's totally doable. Like there are a lot of bit manipulation problems where if you just don't know this thing, then you're kind of, you can't really do it. This one I would say is more doable even if you don't know this. Okay, and now we can code it up. So we're gonna say our result array equals, so the first number is just gonna be prefix at index 0, and then we can get the rest of it, right? So for I in range 1 length prefix, we're gonna say result append, and then this is just gonna be prefix I XORed with prefix I minus 1. And we can return result. Now let's try that. And that works, I think. And there we go. So this is basically as good as it gets for the solution. Everyone's gonna have kind of similar thing. So maybe we'll click until we get a better time or whatever. It doesn't really matter too much. So let's think about the time and space for this one. And for the time, so you could argue it's going to be n log n, because basically when you're XORing, it's gonna you need to XOR bit by bit. So like once a number gets really big, XORing two numbers there's like log n bits compared to the size of the number. But usually, I mean, we can take a look. I think you can see here. So usually the numbers are like, yeah, like they're like a 32-bit number or something. So the size is limited. So if it's like a 32-bit number or 16-bit number or whatever, the XOR is constant time. But if you did have like really big numbers, it would be n log n. But in this case, it's going to be O of n, because yeah, the numbers are like 32-bit or something usually of that sort. And for the space, it's O of 1 because we just have the result. So we didn't really use anything extra. We just have the result, which isn't part of the space complexity. And yeah, that's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.